Really?
What? What? When
Okay, so we're going to start off we're going to finish up Module 4 and start Module 5 today. Module 4. Page 176. Okay, so you're going to do that whole page, 176. For each, in addition to the questions that are there, I've got one more question for both numbers, what is it, 7 and 8? So after you do each part, actually on 7 you can just change part B to this. Okay, so make part B what is the continuous rate? The actual rate of growth? And the 1-year growth factor. And then that same for number 8. The UK problem. So that'll be your part C. Yeah. So then part C for number 8 is the same thing. So that's 7B and 8C. So you're going to add a new question. But then this now it'll be decay. And what is it? 1. That rate, the rate is given to the form is given to this form. What's the form that's given? Okay, so right on X or Y. And then exponential functions. A, B to the, well, in this case t, right? Yeah, but it could be x, right? So what we're given here is a, b to the t, right? So we need to know how these match up, right? How do they match up? A is the same. A is the same. B plug in. B and K are the same. Is that what this is? B and K are the same. So it's A, K to the T. That's the second form. A, K to the T. If B and K are the same thing, then that would be A, K to the T. Is that what it is? No. So how do those compare? It's not A, K to the T, right? You're just saying B and K are the same number. Then the other form would be A, K to the T. So what's it B? What does it match up with? This is the real key thing here. What does B match up with in that second equation? You guys took it down? See? The A's match up. Right? And the T's match up. So what's the base of T? In this one, what is the base of T? E raised to the K. So therefore B equals? Right. Well. Yeah, what is the continuous? B is not a rate. It's not a rate. K is the same. B to the K. B is not a rate. Growth factor. Okay, let me do 7 and I'll put you back to work on 8, okay? So what form are we given here? Which form are we given for this function? Okay, which is what? In general, what's our standard exponential form? A, B to the T. What is A? Starting value, easy, right? What is B? It's the growth factor. It's the multiplier. Every time we advance 1 year, the population gets multiplied by B. So if we advance 10 years into the future, how would we get the new population if we advance 10 years into the future? What about it? Is B to the 10th the new population? What is B to the 10th? What you multiply the old population by to get the growth factors. Multiplication. Growth factors are about what you multiply by to take the old output and get the new output. So if I want to get the population 10 years later, I'm going to multiply by what? Ten? Can I multiply by 10? By what? 10. What's itself? Going to take the old population and multiply it by b 10 times, or times the 10-year growth factor, which would be b to the 10th. B to the 10th. Okay? So that's kind of review stuff. All right? So b is this number right here. Okay, so our other form is a, and I've been writing it this way to really help you. They didn't, though, and that's fair. You need to be able to see it. They wrote just KT. That makes it harder to see, but you need to be able to do it. So, how does this form relate to this form? B equals what? E to the K. So what is the value of B in this problem? What's the value of B in this problem? 1.0362. And from that, we can find what this number K is. And so, if K is an exponent, how do we solve for exponents? This is the exponent of E that gives 1.0362. And that's exactly what logs do. They give us exponents. The exponent of E that gives 1.0362. What's that? So, what is the natural log? Do you know what the natural log is? Log of AC, right? So, it's the same thing. Okay, but what I'm trying to practice this idea of solving for exponents. Okay, just watch out for memorizing rules; it will get you into trouble. Okay, so we want the log of AC, but that is the same thing as natural log of 1.0362. Okay, so what do we get? 0.035. Let's just round it to 6. Is that the right rounding? 0.0356. So now we can rewrite this here as, what's A? I'm just going to leave it as A. I don't want to write that out. To E to the K value we just got. T. These will both output this function, the given one, and this will output the exact same outputs for the exact same inputs. It's the same function, just in a different form. Okay? So, what is the continuous rate? What is the continuous rate of this city's population? Do you know? What's that? He wants K. So he's saying the continuous rate is 0.0356 or 3.56%. That's the continuous rate. The continuous rate is that exponent of E. When you put it in the function, it's a decimal form. When you say it, you often will say it as a percent, okay? So as a percent, the continuous rate is 3.56%. What is the actual rate of growth? Is it 3.56%? How much by what percent does this population grow every year? 3.62%. So our continuous rate is 3.56%. But the actual growth is according to 3.62% per year. Why? So why do we have these two different percentages? What is the continuous rate? Why is it less than the actual rate of growth? Do you remember?
Because that's, so the continuous rate is the one that got divided into 12. Let's say for this one, some months, you divide it by 12. And you're multiplying it that many times in order to do it. Oh no, it's continuous, so you're continually multiplying it
So it's like we broke the year up into how many pieces?
into very,
Yeah, an infinite number, right? So it's like we took the year and we broke it up into an infinite number of pieces. And we said what rate that if we kept compounding every moment would result in a true increase of 3.62%. So the 3.56, when combined with continuous growth, results in a true percent increase of 3.62%. What's the 1 year growth factor? Yeah, that's the B value, 1.0362. Or so, yeah, right. So in the two different functions, you've got these two numbers. So the continuous or the growth factor is B, 1.0. So in this e to the kt form, you have k is the decimal version of the continuous rate. In the ab to the t form, you have the actual growth factor, okay, which is the multiplier for every year to get you the next year's population. So they're very much apples and oranges, this k value and this b value. So you have to really keep that straight. What are the meanings of those? So that's your actual multiplier, your actual growth factor. This is k is 0.0356, which is the continuous rate, which is not what the actual population increases by. Actually, the B is where it shows you the actual percent increase. K is the continuous rate that when combined with continuous growth gives you that growth factor and that actual percent increase. Okay.
so
Yeah, go ahead. Question.
when do you know, because a lot of the problems that we've worked on in the past have just been, okay, this is your percentage, and then that percentage was our continuous rate. So how do you know when you're not working with continuous rate or not? So like, usually the question would have been, the continuous rate is 3.62% per year.
Right.
So the 0.0362 would have been what equal to K.
So you'd start by saying A times what? If they told you that the continuous rate was 3.62%, you would start with A times E to the 0.0362. That's right.
So since they gave us
But they give you the actual rate.
the actual rate,
So that helps you find B, which was actually given here. And so from B, you can find K by B equals E to the K. Okay, so now try 8. Now that you have a little context. So try 8, and then after you finished 8, same thing. What's the actual percent decrease? What's the growth factor? What's the continuous rate of decrease?
let's see.
Okay, I'll make a round of questions. So this is really important stuff. Did you get this? Okay, what about this number, negative 0.0142? What does it tell us about this? What's that? Why is it decay? Yeah, it's negative, so it's decay, first of all. What else? Is it a rate or a growth factor? Is it a multiplier or is it a rate? It's a rate, that's right. So we could write it as a percent. We could say negative, what percent is that? Negative 1.42%? And what percent is that? What rate is that? That's the continuous rate. That's the continuous rate. Okay, so we want to. Oh, is there something in your book right here? Okay, good. So is that a b to the t? A b to the m. Okay, so in that form, what's a? What's b? How do you get it? Yeah, you're just going to solve that right there. That's your b. Your b is e to the k. So you said 0.986? Good, okay. So now the question is, what was my three questions? Continuous rate, actual rate, actual percent change, and 1 month growth factor. What's that? Oh, you actually did year? This is in months now. We can do that after that. Okay. So what's the continuous rate? Okay. What's the actual percent change? So here we have a growth factor less than 1. How do we get the percent change from that? Remember? You got to take 1 minus that. And so it should be something close to this. That's how you can check your answer. We know it's going to be close, but not the same, right? Close but not the same. So what is it? 1.44? So you could say negative, or you could just say 1.44% decrease, either one. So 1.44% decrease or negative 1.44%. Something else? 40. Thank you. Is that right now? Okay, so if you have continuously decreasing at 1.42%, does it make sense that after 1 unit, or after 1 month in this case, it doesn't go down that much? It goes down less than that. Does that make sense? Why does it make sense? Yeah, within that first month, as you start decaying, that amount goes down. So the percent of that amount goes down. So you're not going to quite get to negative 1.42%. And so the actual percent change is going to be negative 1.4%, which we got from B. So what's the 1 month growth factor? That's the multiplier that gets us the next month's what profit. If you have a profit and you want to know what the profit is 3 months later, what would you do? So you have the profit at one time. How would you get the profit 3 months later? Okay, cube the growth factor, and then what? And multiply by 8.3. So I have the profit in a certain month, and I want the profit 3 months later. What will I do? What to the third? Yeah, so I have some profit. Call it just little p. I'm going to add. How do I get the profit 3 months later? That's right. Every month I multiply by 0.986. So 3 months later I'd multiply by 3 times. So there's my profit. That's my profit 3 months later. Every month, what happens to the profit? It goes down 1.4%. Okay, you got to practice this. Okay, I know this is confusing. So make sure you'll have practice in your homework. And then also, I'll put up the web work, which is the online stuff before the next test. There's several problems that help you practice this. So I really encourage you to work on this. Because my experience has been this is confusing for students, especially if you don't practice it. But if you practice, keep practicing what each number means, it'll click. You'll get it. Okay, last chance for questions. All right, so we're going to move on to next module. Okay, so let me just let's do a little review here. So we've been talking so it's not wrong to say that this class is all about one thing. Remember what that one thing is? Did we say what this was? No, the whole class. What's that? Oh, sure, but what ideas, right? What one idea is this whole class could you say it's about? Yeah, that's right. And what is that? Did you remember it? That's it. Okay, so we got one quantity. So we're used to these, like generically, we could say x and y, right? And we show that on a graph with x-axis and y-axis. We're going to be doing some of that in a second here. But we're basically looking at different ways that two quantities could change together. The first way that we looked at was, remember? Oh, that was the second. Proportionally, right? So we talked about proportional covariation, and then we talked about, from that, constant rate of change. And then where did we go from there? So from there we kind of talked about just a symbolic representation, a function representation of covariation. And we did what did we do? We did just the basics, and then we did composition and inverse. And then we did our third type of covariation, which was what? More general than that. Was that exponential growth, right? So there's some coherence to all this. It's not just we're not just flipping around from idea to idea. It's all about learning about different ways that two quantities can change together. Okay? Proportional was a very specific way that two quantities change together. Then we looked at constant rate of change. It was a linear graph, right? That's where we said the changes in the quantities are proportional. And then now exponential growth. What characterizes exponential growth? How do the quantities change together? Based on what? Repeated multiplication of the growth factor, okay? So we're going to look more at kind of just covariation in general here with these bottle problems. So this is where we're going next. So consider that we have a bottle here. Okay? And we are going to put water in it. Okay. Some of you are wishing we put something else in it. Because you're in college, right? Okay, but we're going to stick with water. We want to stay hydrated. Okay, so we're going to look at the two quantities, volume. What's that? A fruit smoothie. Okay, fruit smoothie. So the volume of water that we put in, and then the resulting height okay, so maybe this is milliliters, and maybe this is centimeters, but the units don't matter. So we're going to look at the covariation of these two quantities, how much water we put in, and how height co-varies with that, or how it changes with the volume of water. So the technique to kind of do this and form these graphs is to look at small changes in what we call the independent quantity or the x quantity. So to sketch the covariation, the first thing we're going to do is we're going to consider small increases, small equal increases. In the independent quantity. And that's usually, or that we graph that as x. We have control over how much water we're putting in, independent. So we can put in a little or a lot of water, we have control, and then once we put that water in, the height is dependent on how much water we put in. We don't have control over that. We have control over how much water we put in, and then the height is dependent on that. So we call in this case, the volume of water independent, and then the height dependent. So you're going to consider small equal increases in the independent quantity, and you're going to, let's see, so we're going to, how do I say it? Track each change in the dependent quantity for each small and we can ask questions like, does the dependent quantity increase when we add a little bit of our independent quantity? Does it decrease? Okay. And then we want to compare changes. All right. So the third thing is, how does the next change compare to the previous change for adding the same small equal amount of the independent quantity? So then we want to compare each change to the previous change. This is covariation. This is really getting our hands dirty and figuring out how are these two changing together. That's dependent. So compare each change in the dependent quantity to the previous change. So we do it in this case we're adding water, so we're going to add 1/10 of a milliliter at a time, say. Every time we add 1/10 of a milliliter, we're going to ask, what happened to the height? Did it go up? Did it go down? Did it go up a lot? Did it go up just a little bit? And then, as we continue to do that, each time we add a little bit of water, we're going to compare the change in height to the previous change. Is the change bigger? Is the change smaller? Okay? So here's my straight vertical side bottle. Okay? It's just like a can. So it's a bottle just like a can of Coke or whatever. So I'm going to put in my first little bit of volume. What's going to happen to the height? It's going to go up some amount, right? So as I put in that much, the height starts at 0. It's going to go up some amount. Okay, now I'm going to put in the next same equal amount of water in the bottle or in the can. What's going to happen to the height? It's going to increase. Now compare it to the previous change. Will it be the same, more or less than the previous one? Same increase. So if I went up this much the first time, now I'm going to go up that same amount the second time. Okay, I'm going to add the same small equal amount. It's tedious and boring, but if you rush to judgment and you try to make these generalizations too quick on a harder one, then you're not going to get it. Okay, so I'm going to add the same small amount. What's going to happen to the height? Will it go up or down? It's going to go up. How does it compare to the previous change? Same. What kind of covariation is this? Yep. Not only, yeah, it's a constant rate of change. Constant rate of change. And in fact, because it goes through 0, 0, it's also proportional. Okay? Proportional. The height is proportional to the volume of water in there. And that's only because it goes through 0, 0. But because it's linear, it's constant rate of change. Okay, so this is what we want to do. We want to add equal amount. If it's a bottle problem, we're going to add small, equal amounts of water, and then we're going to track what does the height do, and how does each change in height compare to the previous change in height. Okay, so I got to, first of all, okay, so I've got, is there more? Need more? Who needs more? All right, so let's do, we'll do one together here. Let's do the second one together. It's not letting me. Let's try this. No, I don't want that. This. There we go. So we're going to do this one. And now they're saying the small amounts that we're doing are cups. Okay, we're going to add 1 cup at a time. So is that the middle one in your paper? Okay, so what's our strategy? What do we do first? Add a cup. What's going to happen to the height when we add a cup? A lot? It's going to increase a lot or a little? The height will increase a little. So here's showing that we're going to add this volume of 1 cup right here. And as we do that, the height's going to go up this much. Okay, what do we do next? We're going to add another cup. What's going to happen to the height? It's going to go up. Well, the change in height, that new change in height, how does it compare to the previous change in height? Will it be more, less, or the same? Most people are saying more. Why more? Okay, so the bottle narrows, and so, do you see that? Can you see that on the graph here, that this change, the new change, is a little bit more than the previous change? Okay, we're going to add another cup. What will happen to the height? It will increase. The height will increase. What about the change in height? Does the change in height stay the same, decrease, or increase? The change in height. So not only does the height increase, but the change in height increases. You get a more of a jump in height than the jump that you had before. So what does that look like on the graph if you track that out? So here's from our first, but then when we got to the second change, there's a little bit more. And now for the third, It's still a little bit more. Constant rate of change? What kind of rate of change is this? So the changes are doing what? Each change is more or less than the previous change. Each change is more than the previous change. So what is the rate of change doing? What's that? Well, not necessarily exponentially, but just in general, what is the rate of change? Is it steady? Is it constant? How is it varying? Well, is the rate of change not staying the same, so it could only be doing one of two other things. It could be slowing down or speeding up. So if the changes are increasing, so where's our next cup? Where are we at? Cup 3? So cup 4. Each time I add a cup, the height increases, but the change in height increases also. Do you see it? Each one of these little changes is greater than the previous one. What's going to happen when we get to this part of the bottle? Yes, fit graph to screen. That works. Okay, so what's going to happen? We're going to get to a certain point. I guess it's at cup 9. It jumps all the way. Okay, but anyway, so there's a certain point where it's going to, the covariation is going to change to what kind of covariation? It's going to be constant because with each amount that you add through this part, you're going to get the same change in height every time. Up to that point, the changes in height were increasing. Okay, so why don't you try number 3. Do it 1 cup at a time. 1 cup at a time. Ask yourself, what happens to the height? What happens to the change in height compared to the last change for cup number 3? Don't rush to judgment. Do it 1 cup of water at a time. Okay, with each cup, what happens? Does the height increase or decrease? The height. With each cup that you add, the height increases. The height increases. What about the changes in height? You can see it here on the height graph, on the height axis. Each change is less. So the height is increasing, that's key. The height is still increasing. We're adding water, so the height's going up. But the changes in height are decreasing, and you can see that there. So then what about the rate of change? Watch the H go up the axis. If the changes are decreasing, then what about the rate of change of H? What about the rate of change of H? the rate of change positive or negative? The rate of change. Positive, because the height is going up. The height is going up. So we have a positive rate of change, but it's decreasing. It's going up, but it's decreasing. The rate is decreasing because the changes decrease with each cup of water that you add. So what does the graph look like? So this is showing decreasing changes in height as the height increases. So it's a decreasing rate of change. Okay, homework's due Wednesday. See you then. Just hold on to it.